Morning folks, we're going to try and finish off sequences and series this week. So essentially what we're looking at this week is a few little bits of notation. The first one of these is this little Greek letter sigma, which is used as a shorthand for summations, and all you've got to be able to do is to interpret something like this, to write out that as a sum and to work out what it might be. So let's get through the bits of it. The first thing we've got is this I equals 1 here. What that means is that we need to start at I equals 1. The number at the top here, the 5, tells you where you need to end, and this, the I squared, is basically a formula. It's what you're going to substitute those values of I into. So if we were to write out this sequence here, well, we'll take our 1 and we'll sub it into I squared. That'll give us 1 squared, and then we'll go all the way from 1 up to our end number 5. So our next number would be 2 squared, and 3 squared, and 4 squared, and 5 squared. Obviously you could then work out what that is, but I'm going to leave that up to you. The point is to interpret what the sigma notation means. So again, second sequence, start at 1, end at 3, and then this is the formula that we're going to be putting those numbers into. So we'll do 1 plus 1, because sub in t equals 1 to the power of 1 as our first term, and then 1 plus 2 to the power of 2, and then 1 plus 3 to the power of 3. And you might want to actually tidy this one up a little bit. We could work out that this is 2 plus 9 plus 64, etc., etc. Now, sometimes this sigma notation is used to disguise arithmetic and geometric questions, essentially. Let's look at these two as examples. All you've got to do is plug in the numbers they give you and try and recognize the sequence they have. So our first term here is we're going to sub 1 into here. So we're going to do 7 lots of 1 minus 1, and then we're going to do 7 lots of 2 minus 1, and 7 lots of 3 minus 1. And this sequence keeps going all the way up to 7 lots of 15 minus 1. Now, that looks painful to sort of add up, but what we can do is work out what the individual terms are and see if we can spot a pattern. This first term is just 6, this second term is 13 and 20 and so on. Don't really care about the last term once we've spotted the pattern. And all we're doing here is adding 7. So this is an arithmetic sequence. Specifically, it's an arithmetic sequence where A equals 6, where D equals 7, and where N equals 15. And if we wanted to work out that sum, well, we could just use the Sn formula, that this is n over 2 lots of 2a plus n minus 1 lots of d. So let's do that. We want 15 over 2 times 12 plus 14 times 7 at the end there. And that's going to give us 825. Cool. So let's look at the second one. This again starts with b equals 1, goes up to 20, so we'll sub in 1 first. This will give us 0.5 times 2 to the power of 4. Yeah, 1 plus 3 is 4. And then our next term will be 0.5 times 2 to the power of 5, and then 0.5 times 2 to the power of 6, all the way up to 0.5 times 2 to the power of 23, if we sub in b as 23. So again, that looks very, very painful. Let's work out what the individual terms are. This is a half of 16, so that's 8. Half of 32, half of 64, and so on. And again, I don't really want to work out that last term if I don't have to, because I can identify that this is a geometric sequence. We are multiplying by 2 each time. So it's geometric, a equals 8, r equals 2, and n equals 20. So again, we can use the formula here. We can say this is a lots of 1 minus r to the n over 1 minus r. We can say this is 8 lots of 1 minus 2 to the 20 over 1 minus 2. And that'll give us a fairly chunky answer of 8,388,600. So you see there, we simplify the terminology and make it into a question we've already done. So it's worth saying that these sigmas don't always have to start with r equals 1. They can start with any number they like. So in this case, we're starting with r equals 5. And all that means you've got to do is to start by substituting 5 into the sequence. So this would go 17, and then 21, 25, etc., all the way up to 37. So one way of getting the answer to this question would just be to add those numbers up and get 162. Another option would be to look at those numbers you found, say, okay, well, this is an arithmetic sequence because it's going up in 4s, where a equals 17, d equals 4, n equals 6. Now be careful here. Some people will say n is 5 because 10 minus 5 is 5, but you've also got to count the term you started on. There are actually 6 terms in this sequence, and then we could use the Sn formula to get to 162 as well. A third option, though, is to use this complicated looking formula up here, which is that if we wanted to find the sum from the 5th term to the 10th term, then what we would do is we would take the sum of all 10 terms, so r equals 1 to 10, and then we take away from that the sum of the first 4 terms, and that should leave us from the 5th to the 10th. Now, in this case, this isn't a very sensible way of doing it because this is a sequence that we can write out in its entirety without too much effort, and we can use arithmetics quite easily as well. But it's worth knowing that's another option, because the important thing about this is it simplifies it to just Sn situations. We're doing the sum from 1 to n. Let's look at another example of where this may be some use. We've got here, we want the sum from n plus 1 to 2n of just the number 2. Now, this is a weird sort of sequence, really, because what we're saying is the first term is 2, and the second term is 2, and the third term is 2. It doesn't actually matter what b is, because it's not part of the actual formula. And the last term, amazingly, is 2. So the only question there is, well, how many terms were there? Here, we said there were 6 terms, and a way of getting that was doing 10 minus 5, which is the start and end of our sequence, plus 1, because we've got to account for the starting term. We can do the same sort of thing here. So we can say that the number of terms is equal to 2n, take away n plus 1, plus 1. If you do that, you'll get 2n minus 1 plus 1. So there are actually just n terms in this sequence. So all we're essentially saying is, what is n lots of 2? And that's 2n. We could approach this in the formula sort of way if we weren't feeling good about counting those. We could say, well, this is the equivalent of going from 1 to 2n of just the number 2, and then taking away from n plus 1, from 1 to n, again, just of 2. And then it's maybe easier to see. We've got 2 lots of 2n, take away 2 lots of n, which is going to give us 4n, take away 2n, which again will give us that answer, 2n. So yeah, if the situation just looks weird, just plug numbers in and see what you get. Okay, so the last bit of sequence notation that we need to look at to finish this chapter is recurrence relations. And recurrence relations you've encountered slightly in GCSE, iteration I think was what you called it. And it's the general idea that we can define a sequence by saying a initial term, a point where we start, and a term-to-term rule. So how do you get the next one? And it's essentially a formula to plug something into repeatedly. Let's look at this as an example. We've got our term-to-term rule is to do 3 lots of the previous term, so 3 times un, minus 4. And we're starting with 3. So there's our u1. So if we wanted to find u2, we should do 3 times that 3 and take away 4, which would give us 5. So our second term is 5. If we wanted to find our third term, we do 3 lots of our previous term, so 3 lots of 5 this time, and take away 4, and this will give us 11. If we wanted to find our fourth term, we do 3 times 11, take away 4, which is 29. You get the idea. Now that sequence isn't arithmetic, it isn't geometric, it's just a sequence defined by this particular recurrence relation. Do the same thing here. We start with 3, and then the formula this time uses the previous term twice. It goes un squared, take away un. So we're going to start by doing 3 squared, take away 3, which is just 6. Okay, maybe there's a pattern here. u3 is going to be 6 squared, take away 6. So it's going to be 30. U4 is going to be 30 squared, take away 30, which is 870, and no, this is getting very, very big, very, very fast. Again, not arithmetic, not geometric, but it's a sequence and it's defined and we can say what it is. Something they like to do with recurrence relations is to introduce a little bit of algebra, because what is maths without it? So let's look at a full example here. We've got a sequence defined by an initial term and a term-to-term rule, and the term-to-term rule seems to be saying square the previous number, take away 2. And we're starting with k. So let's find the first 3 terms of the sequence. Well, the first term is k, that's straightforward enough. And then let's use our term-to-term rule. So if we want to get u2, we need to do, well, a2 as they're calling it here. We need to do previous term squared, take away 2. Okay, so it's just k squared, take away 2. If we want to get the term after that, we need to do the previous term squared, so it's k squared minus 2 squared, take away another 2. Now, I probably want to tidy that up a little bit. If we expand that bracket, and then take away the 2, we'll get ourselves to k to the 4 minus 4k squared plus 2. Okay, it only says to do the first 3 terms, so we don't need to keep going, which is good, because that looks like it's going to get ugly fast. Let's go on to part B. It says given a3 is equal to 2. So our a3 was this one here, was the third term that we found. It says we need to find k. So what we should do is set that equal to 2, and we should try and solve it to try and find what k actually is. We need to subtract the 2 to start with. Always want to make one side equal to 0. That's good. We then probably want to factorize this, so we can take out a factor of k squared, and that will give us k squared minus 4 inside the bracket. We then want to, let's carry on over here, we then want to factorize that k squared minus 4, that's going to be k plus 2k minus 2. So that means either k is 0, or k is minus 2, or k is equal to 2. Now it says k is negative, so we're going to have to take the negative result. K is equal to minus 2. Okay, great. Let's just box that off. Third question. Using our value of k, we want to find the sum from I equals 1 to 10 of our AI. So we're now introducing some sigma notation. So I think a sensible thing to do here would be to write down the sequence now we know what k actually is. We knew the first term was minus 2 because it was k. Our second term is k squared minus 2. So that's minus 2 squared is 4, minus 2 is 2. Our third term, okay, this is getting a bit awkward to sub into, so let's go even simpler than that. Let's go back to the actual recurrence relation, which said to get the next term, you square the previous term and take away 2. Let's just use that. 2 squared take away 2 is 2 again. And it's 2 again, and it's 2 again, and it's 2 again. After our initial term, everything else is just 2. So if we wanted to add up the first 10 terms here, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those two will cancel out with each other, and we'll just be doing 8 lots of 2. Our sum for our first 10 terms is just 16. What is A100? Well, that's the 100th term in our sequence, and we know it just repeats the number 2. So it's 2. What is the sum of 1 to n of our sequence? Well, let's think about this. If we want to add up 1 to n here, we're doing minus 2, plus 2, plus 2, and then eventually plus 2, and we're doing that n times. So all of these, there are n of them. We know these two are going to cancel out, so ignoring them, there must be n minus 2, lots of these 2's. So our sum is going to be 2, lots of n minus 2, which is just 2n minus 4. Now the last words we can introduce here are increasing and decreasing. A sequence is increasing if every term is greater than the previous one. So if I had a sequence that went 2, 3, 4, 5, or if I had a sequence that went 2, 5, 15, 302, those would be increasing sequences because they're getting bigger. You can write this more mathematically like that. Decreasing sequence would be one that's getting smaller. So 5, 4, 3, 2, that's a decreasing sequence. Sequences are periodic if they repeat. So if I had a sequence that was going something like 3, minus 3, 3, minus 3, dot, 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 that's a periodic sequence. The amount of terms it takes for the sequence to repeat is called its order. So because this takes 2 turns to get back to 3, this has got an order 2. If I had a sequence that went something like 0, 2, 4, 0, 2, 4, then that would have an order of 3 because it takes 3 turns to repeat a number. Lastly, sequences are convergent if they tend towards some sort of limit, and they're divergent if they do not. So all the sequences we looked at here are divergent sequences because they're getting bigger and bigger and bigger, or smaller and smaller and smaller. If you had a sequence that was going something like 1, and then 0.1, and then 0.01, and then 0.001, and etc., that would be a convergent series, a convergent sequence, and it would be tending towards 0. So yeah, I don't think they're actually going to ask you about convergent, divergent this year, but they might do next. So we could look at some sequences that are phrased in sort of different ways, and we could say, are they increasing or decreasing or periodic? I would like you to try these first, so I'll just assume you're pausing the video now. And welcome back. Let's have a quick look here. So our first one, pretty obvious, that is increasing. It's going up by 4 every time. For the next ones, we actually need to work out what the series are. This starts with a 3, and then the recurrence relation says square previous term. So 9, and then 81, and then 243, etc. That is an increasing sequence as well. Our third sequence starts with a half, and then squares the previous term. So that would go to a quarter, and to an eighth, and to a 16th. And this is definitely decreasing. It's also convergent because those numbers are getting closer and closer to 0, but that's not what the question asked, just wanted to point it out. Our next one, we start with 1, and then we do our number squared, take away 1. So if we do 1 squared minus 1, we get 0. And if we do 0 squared, take away 1, we get minus 1. And if we do that squared minus 1, we go back to 0. And then if we do that squared, take away 1, we go back to minus 1. So this is following a pattern after the first term of just going 0, minus 1, 0, minus 1. This is a periodic sequence, which I can't spell. And it has an order of 2 because the zeros, the minus 1s, they happen every 2 turns. Okay, lastly, we'll assume this is in degrees, by the way. This isn't a recurrence relation, although it looks similar. This is just an nth term. And it's telling us to get the nth term, you just do sine of 90n. So we'd start by summing in n equals 1. We get sine of 90, which is equal to 1. Then we'd sub in n is 2. And we get 0. Then we'd sub in n is 3. We get minus 1, and so on, and so on. Now, this one is actually, it's obviously periodic because something is repeating. But what do you think the order is? Is it 2? Because 0 definitely repeats every 2. But no, the whole sequence needs to repeat. So it's actually order 4. And we have like that one goes to that one, 0 goes to 0, and so on. I think you can make the mistake of going with an order 2 there, understandably. All right, let's finish this off with a couple of exam questions. You tend to see more arithmetic and geometric, but obviously you will see the odd recurrence relation. We've got a sequence defined by u1 is 3 and un plus 1 is this thing. So let's work out our values. So u2, according to our thing, is equal to 1 minus 1 over our previous term. So 1 minus 1 over a third. So that's going to be 2 thirds. Our third term, our u3, is going to be 1 minus 1 over 2 thirds, which actually gets you to minus a half, because you end up doing 1 minus 3 over 2. And our fourth term is going to be 1 minus 1 over minus a half, which gets you back to 3. And then obviously it'll repeat, it'll go 2 thirds minus a half, 3. So the behavior of our sequence is that it is periodic. That's enough to get you to the mark, but you could say it's got order 3. Let's look at a slightly more in-depth version here. We've got our sequence un defined by this recurrence relation, and we've got some algebra in it, which is excellent, and we're given the first 3 terms of our sequence, our u1, our u2, and our u3. It says we need to show that p equals 0.6 and find what q is. So we know that U1 is 100, 200 rather, and we know what U2 is 150, but we could put it in terms of this formula as well. So we know this would be P lots of UN, so 200P plus Q, and we know that's equal to 150. We can do the same sort of thing with U3, and we know this is going to be 150 lots of P plus Q, and we know this is equal to 120. Then we can do a classic simultaneous subtraction there, and we can say so 50P is equal to 30, divide by 50, P is 0.6. Now if we want to find Q, we can obviously substitute that back in there, so we can say, okay, so 200 lots of 0.6 plus Q is equal to 150. So that's what 120 plus Q is 150, so Q equals 30. There we go. Nice 5 marks. If we look at the sequence as well, we can actually see, I think, is this a geometric sequence? Maybe not quite, no. Okay, it says to find the value of U4. So for U4, we're going to need to do P lots of UN, so we're going to need to do 0.6 lots of U3 and plus our Q plus our 30. So that's going to be 0.6 lots of 120 plus 30. It's going to be 72 plus 30 is 102. And it says the limit as it tends to infinity is L. We want to work out what that L actually is and how we can get it. So how can we do that? So we can use a little bit of a trick here. If we've got a limit of L, we're saying that eventually this tends towards L, then it should be the case that if we put that limit into the sequence, if our UN was L, then they should be the same value as each other. If this is our limit, that's not going to be any different. Our UN plus 1 is equal to our UN. So instead of writing P, we'll write 0.6. Instead of writing Q, we'll write 30. And then we can just solve this equation. So this will give us 0.4L on the left, 30 on the right, and this will tell us that this sequence tends towards 75. Now, if you didn't feel very confident in that sort of approach, another way of getting the sum to infinity would be using the limit to infinity would be using the answer key. So one thing I could recommend is this. We'll do, type in your calculator 200 equals, I'll give you 200 on the machine, and then you want to do the formula repeated. So we want to go 0.6 answer plus 30. And then we just want to repeat that process. So if we do that, you should get 150, 120, 102, 91.2, and you can keep pressing equals for a long time. And as you do that, you'll see that your numbers are getting closer and closer to 75. Try that out for yourself because it's a good way to convince yourself that you're right.